Is the only purpose of a building to provide a pleasant and comfortable living or working space? And what about an industrial plant or the power grid? We think differently. With smart infrastructure combining the real and digital worlds across energy systems, buildings, and industries, making residential, industrial, and business environments better, making them more efficient, more human-centric, and in doing so, making everyday life better for us and for future generations. In other words, smart infrastructure is sustainable infrastructure.
I'd like to welcome you to today's webinar and thank Siemens for sponsoring today's session. A few items before we get started. We will be holding questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button. If you happen to be experiencing technical problems during the webinar, please use the Q&A button to inform the panelists, and our producer, William, will assist you. The presentation is being recorded and will be available for viewing in about a week. And in terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And if you are a certified CXA or EMP, your CEUs will be automatically uploaded to your respective portals after the webinar. Today's webinar is a unified approach to HVAC optimization and maintenance with Jesse Kraft, Energy Services Portfolio Manager for North America with Siemens Smart Infrastructure. Jesse leads the portfolio team for Siemens Energy and Performance Services Group in North America. He and his team are responsible for developing and supporting the deployment of technology offerings designed to help customers achieve sustainability and efficiency goals in complex buildings. Jesse has been in the energy efficiency industry for over 15 years, starting as an energy engineer conducting audits and designing optimization strategies for individual customers across a wide array of vertical markets and systems. He's a licensed professional engineer and holds a master's degree in mechanical engineering. Thanks again, everyone, for joining us. And with that, I'll let Jesse kick us off.
All right. Thank you, Karen, for the introduction, and welcome, everybody. So today I'm going to be talking about an approach, a unified approach to HVAC optimization and maintenance. I have today's agenda broken up into three sections. First, I want to share my understanding of why this topic is important. How does the design of optimized control sequences impact the ability to maintain that performance over the long term? Second, I'll share a perspective on two of the tools that we can use to address these deficiencies. Digital twins and machine learning are two of the emerging software solutions to the problem, and we'll discuss how that impacts optimization design. We'll also talk about the role that process and expertise will continue to play in the operation and maintenance of high-performing buildings. Before we dive into it, I believe we have a poll question. All right, so our poll question is asking your opinion on fault detection services. And I'm going to be very interested to see what the results end up being. All right, so we have our results, and it looks like about a third of folks have never used this type of service or don't know what it is. So we'll certainly talk about it. I'm also glad to see that nobody says that it doesn't work and we find no value. But I would say that the spread of results amongst those who have used it is about what I would have expected, right? For a lot of folks, it works very well. And then some folks are seeing the same issues over and over again. Then there are folks that are finding issues at the start, but find fewer issues now that we fix things. And we'll talk about what the difference is between the people who have seen result number 2 and result number 3 in a little bit. So here we are. That poll question out of the way. So let's really underline the importance of building maintenance. And I use these two charts in almost every presentation that I do. right? So these are from data that I put together that is published by the U.S. Energy Information Administration. This is data from the Commercial Building Energy Consumption Survey, or CBEX. If you have ever gotten an Energy Star score for your building, that score, that rating, was based on the result of this CBEX data. This survey is conducted every few years, and it gives us information on the state of how energy is being used in buildings. But what we're doing here is we're looking at how that result is evolving over time. So it tells us a story about how existing building stock is evolving. So let's look at these two charts. I include both because I want to rule out some universal factors that might explain changes like climate change or updating building codes as an underlying cause, and really want to zero in on what are the differences between the buildings that were constructed in the 60s and ones that are newer, constructed in the early 2000s. So this chart on the left is for buildings that were constructed in the 60s. I think of these as the control group for our analysis. What we see is, I think, the expected result, which is that energy consumption related to HVAC and lighting is being reduced over time. You know, this is the hard work of traditional energy engineering, going out, conducting audits, and advising building owners on how to implement retrofits. So this is converting pneumatic controls to digital controls, changing out old fluorescent lights for LEDs, converting constant volume systems to variable with the emergence of very efficient variable frequency drives. So as a result, we see a nice reduction in both lighting and HVAC energy usage in this older building stock. That is not, however, what we see in our newer buildings. Improved energy efficiency standards for buildings, largely driven by ASHRAE, if we're familiar with the 90.1 standard, and folks following the guidance of the US Green Building Council, resulted in new building stock that was significantly more efficient than older buildings on day one when they first opened. However, this improvement in efficiency has been achieved at the expense of complexity. So all those things that we were putting in, the digital controls that enable dynamic resets, variable flow systems, and even more complex systems like chilled beams, these all deliver less energy usage if maintained and operated properly. However, that requires an investment in technology and training in order to make them continue to work the way they're supposed to. However, building staffs have gotten leaner, they've turned over, and we have less experienced folks operating these buildings. And as a result, these buildings are backsliding. What we see is, particularly in HVAC, because lighting has gotten more efficient, right? We've still done the same LED changeouts on lighting, but the HVAC in particular, that energy usage has gone up over 20% since the day these buildings opened. Now, the good news is that these buildings are capable of more, right? Getting that efficiency back is not going to require expensive retrofits of the underlying mechanical components, but we have to think about a different way of maintaining and optimizing these buildings. So why is this happening? So I call this the four horsemen of optimization, right? So we want to improve the operation of building systems. It requires that we tackle surprisingly complex optimization problems. However, we also need to consider how this complexity is influencing the operability of our buildings. So let's look at the top two problems, right? These are what I call the fun problems to solve. Engineers and data scientists love coming up with ways to solve these problems. The bottom two problems are our stumbling blocks. These are why the cool solutions that we want to develop and deploy in our building systems often end up failing. So I'm going to talk about each of these and give an example or a couple of examples of where we're going to see these in our buildings. So first, let's look at forward prediction. Building controls are by their very nature backwards looking. You know, a control device does not start modulating until a value has deviated from set point. You know, my air conditioning doesn't turn on in my house until it gets too warm. That means if a disturbance is large enough, the error that can result can be large enough that we get complaints or operational issues. So let's consider trying to control the temperature in a zone when a cold front comes through. right? If that cold front is particularly severe, the heating load on the space can be large enough that I'll get cold complaints, right? And what I want to do is I want to preheat that space to minimize the impact of that cold front coming through. If I know that disturbance is going to occur, then I, as an operator, might want to preheat my building, or an optimization algorithm could do the same thing. It could take steps ahead of the event to prepare for it and minimize the impact of the disturbance while using the minimum amount of energy in order to do so. So that's the example we see here on this chart, right? We've got the optimization algorithm is changing the set point in the space from 70 up to 72 degrees, a small change to begin warming the space up. And then when the cold front hits, we keep that temperature set point elevated until the system starts reacting. And then I drop back down to 70 where I want to be, and my control moves on, and nobody was the wiser. The next example of an optimization problem that's, let's say, a fun one to solve is a nonlinear optimization problems. Reducing energy is pretty straightforward when I know which direction I want to push. So, for example, I know that slowing down a fan will result in that fan consuming less energy. That's pretty straightforward. However, there are many complex systems where the optimization is nonlinear. So for example, let's look at this chart here of how supply air temperature control changes the energy usage of an air handler. If I have very, very warm supply air temperature, say 70, 75 degrees, and I want to cool down a space, that air is not really doing any cooling. So as a result, what will happen is all my VAV boxes will open wide up, my fan will go to maximum energy, and I'll still have hot spaces. Right, so I'm all the way off the right of this chart. So clearly I want to reduce that supply air temperature, right? I want to drop that from 70 to 65 to 60 to 55. As I make that air cooler, it becomes a more effective medium of cooling. I need less of that volume to deliver the cooling to my space. So my fan energy starts coming down. We get to the nonlinear optimization because we use the same systems to ventilate our spaces as we do to heat and cool them. So that fan hits a minimum speed that it won't go below because I need to continue bringing fresh air into the spaces where people are as well. Now what happens if I make my air colder is I start simultaneously heating and cooling. In fact, I find many buildings that I go into in the middle of the summer where either the heat is on or certain office occupants have put space heaters under their desk because they're so cold in their offices. So this is the type of problem that is too complex for traditional optimization approaches to solve. Now, where do I start getting into trouble on the other side of the circle? That's where we have maintenance and operations concerns. So let's consider an optimization strategy like static pressure reset that relies on feedback from zones to decide whether to increase or decrease the static pressure set point. If that feedback is bad because the devices don't work correctly, the strategy fails, right? If I'm controlling to my worst case damper position, but my worst case damper position is always 100% because the device is broken or the box is too small or someone put in an unachievable set point within a space or the load is higher than it was designed for, then that strategy is never going to work. It also introduces the idea that on the flip side, what if my optimization strategy could help me determine which zones have failed or which ones are driving the reset and are most critical to investigate? And then the last one is consider the role of the operator. I have a colleague who likes to say that if the building automation system is too complicated, then what you end up with is just a series of on-off buttons. If operators do not understand what a building automation system sequence is doing, it is only a matter of time before control sequences are an override. Here I have two real quotes from actual optimization projects that I've worked on in the past 6 months. So in the first one, the customer has mentioned that he does not think the boardroom is operating correctly The air handler serving this space is maintaining a discharge air temperature of 59 degrees. Can we make it lower? And on the right-hand side, the optimization algorithm is adjusting the static pressure and reducing it too much, whatever that means. The static pressure is down to 0.8, which is not correct. So what is being communicated here? Are these actual errors or issues with the optimization strategy? Are they entirely unrelated? If I can't figure it out, then the building operators have no chance. The algorithm needs to be designed such that the answers to these questions are obvious. At the same time, we have to understand that building operators have many competing priorities, and keeping the optimization running is not going to be at the top of the list. So let's think about our definitions of maintenance and optimization. When we're maintaining a system, we want to address deficiencies in the mechanical or control system that prevent the HVAC components from operating properly. When we're optimizing the system, we're changing the physical design or the control sequence of the building system to achieve improved outcomes at reduced cost. So how do I maintain a system if I don't understand how it's supposed to operate? Right? If I put in a very complex optimization sequence, how does the maintenance know what it's trying to achieve? On the flip side, complex systems that are designed to achieve efficiency will not deliver the expected results unless they are properly maintained. So we need to add to the existing systems and avoid repeating the same mistakes. So the path to achieving this dual outcome is through the use of operational digital twins. So here I want to make sure that I don't veer into the realm of buzzwords and make sure that we all understand what I'm talking about, because digital twins are definitely one of those phrases that's been out there in the industry for a while and means a lot of different things to a lot of different people. So a digital twin, put simply, is a digital representation of a real physical system. It's distinct from a simulation in that it incorporates real operational data into the analysis. This type of software can be used both to optimize systems, either through assisting in sequence design or through actual closed loop operation, as well as providing the transparency and maintainability that will help retain the benefits over time. So let's break this down a little bit more. In talking about the capabilities of an operational digital twin, there are three categories of value. So the first is this one at the bottom, which is customer information or transparency. In this mode, the digital twin can explain what actions are being taken and why. For example, what are the key parameters that an optimization algorithm is responding to? What devices are in a fault condition? What is the next control action that's going to be taken? What is the next piece of equipment that's going to be turned on or off? A digital twin should be able to populate a dashboard explaining current and upcoming actions so that there are no surprises to operators. The next category is maintenance, and I've got this broken down into three types of maintenance. That's maintenance of controls, equipment, and optimization. I'm going to talk about these in some detail, but what we traditionally do with rule-based fault detection, which most of you on the call have some experience with, that maintenance of controls is really that traditional rule-based fault detection, is a value at its set point. When we talk about maintaining equipment, we want to understand when that equipment is underperforming. A value might be at its set point, but the device which controls that, like the fan, is working much harder than it should to achieve that outcome. And then the last one is maintaining the optimization, right? A value might be at its set point, but is that set point what it should be per the optimized sequence. Then we get into optimization. So there's what I call traditional optimization, which is this is creating new sequences of operation that run directly in the controllers. So I use the twin to evaluate a new control sequence, and I directly program that into the system, and it runs the new way. I might also add new sensors and devices to enable that sequence. And I can use the digital twin to do a what-if analysis of these different sequences. I could also take a next step, perhaps enabled by machine learning, to go all the way to closed loop control. This would be where we take in all the data from these parameters and not only make suggestions of what a new sequence would look like, but we actually implement it. Now here you got to be careful, right? You don't want to directly command end devices, but you can move those set points around like I showed in some of the examples. And then the last type of optimization is flexibility. So this is enabling the building to respond in real time to things like real-time pricing signals, demand response, market participation of our assets in our buildings. Right? All of these are potential capabilities of a digital twin. So let's go through some examples. This is going to be the most technical series of slides. Hopefully you all stay with me and understand here what I'm going for. So that first type of maintenance is the controls maintenance. That's our rule-based fault, right? When we have a prescriptive operational rule that is violated. And the example I typically use is that a value deviates from set point. So here I have a schematic of the condenser water system of a chiller plant. I've got 4 chillers, 4 pumps, 4 towers. I've got a couple of set points and a couple of control devices here. So let's compare our observed values to set point. Here I see my condenser water temperature and my condenser water flow are both at their set point. This means that this portion of the control is operating as intended. So no faults have been reported. Let's go one level down and let's look for sequence faults. This is an indication that the control sequence is not working correctly, even if the underlying control devices are. So again, a value may be at set point, but is that set point what it's supposed to be? In this example, we can see that the observed condenser water flow is not at the modeled set point. So the value that the digital twin interpretation of the sequence of operations would have anticipated and the actual condenser water flow set point are different. So what causes a sequence fault? Well, the most common culprit is operator intervention, right? When you see a point in override. So the set point is supposed to be 2500, 2600 GPM, but the operator has interpreted an operational issue was occurring as a result of that set point and therefore changes it. Now, I've worked with a lot of building operators, and what I'll tell you is that if they're wrong about that set point being the problem, they do not go back and release the operator override. They move on to the next thing. So this is why it's very common in systems that have been optimized to find that basically everything is an operator override. We might also find that the commands of the end devices directly are an override, or some other parameters of the sequence have been modified as well. This can be a result of insufficient operator training or insufficient transparency into the way the system is supposed to operate. But there may be other issues. Things may have changed in the building that mean that that set point really was causing a problem. Honestly, it can't be ruled out. But the building operator needs to be a partner in maintaining the performance of the building in order for any advanced strategies to be successful. The next example is performance faults. These occur when the equipment is working harder than expected to deliver the output. So now let's consider a system where the set point is being maintained and the set point is where it should be, but the pump or fan that is delivering that output is running at a higher speed or consuming more energy than it should. So in this example, we see that condenser water flow is near set point, but instead of a single pump running at 54 hertz, which is what the digital twin expected, we have two pumps running at 35 hertz. This means that the pumps are delivering less water than the digital twin anticipated, so the sequence had to start a second pump in order to get us up to set point. So what could cause this to occur? A lot of different things, a lot of different possible root causes. One of the major ones is unknown loads. Early in my career, I had a mentor of mine describe a situation where they spent hours tracing down ductwork in a ceiling looking for issues and found that at the end of a long ductwork run, the duct hadn't been capped off and was blowing conditioned air directly into the plenum. Right? This would be an extreme example of an unknown load. Right? Turned out I was cooling the plenum all this time and didn't realize it. More common examples are closed off balancing valves, right, where we've installed VFDs to be able to modulate the flow, but never opened up that triple duty valve that was there originally to get the flow where it was supposed to. Maintenance issues is an obvious culprit as well. You can have clogged pump strainers putting additional pressure drop on systems, fouled heat exchangers reducing heat transfer in coils. These would all show up as performance faults in a properly configured digital twin. The digital twin also allows you to go beyond advanced fault identification and into fault prioritization. In this example, we see results from a digital twin that not only counts the frequency of individual faults, but also categorizes them based on the size of the anticipated energy impact. The reason it's able to do that is because rather than a strict rule-based fault approach, we're using the same model that would tell us how to optimize the system to tell us if it's working correctly. It is therefore doing real-time or close to real-time calculations of energy impact. Having the energy impact calculation embedded into the fault engine allows us to more quickly prioritize issues and weed out false positives or nuisance issues. So I've talked a little bit about digital twins. Let's also talk about the potential impact of machine learning. Machine learning, in addition to enabling new types of optimization, also enables new types of fault identification and understanding of how our buildings are performing. So here I'll provide a simple example that I'm going to tie back to one of our operability issues from earlier in the presentation. So here we have a table of room temperatures and set points, along with an indication of whether or not a fault condition has been triggered for this space. The presentation of the faults here has been simplified to just a yes/no state in order to illustrate how the faults might be investigated and prioritized. Based on only this information, it is likely that I would prioritize investigation of VAV box 1-7 because it is the box with the highest temperature deviation and also that has a fault condition. So let's define a new concept that we have in machine learning optimization of VAV systems called a learned temperature range. So a learned temperature range is a statistical analysis that a machine learning algorithm can perform to learn the typical performance of an individual zone. This value can be used as an input to a closed loop optimization algorithm, or it can be used as part of a diagnostic strategy. This is calculated by observing the temperature range over a period of time, excluding statistical outliers also excluding periods when the system is not functioning properly, and then creating an understanding of how the temperature within this space typically varies. So functioning properly means we look for control devices being at their limits, dampers or airflows or heating valves that tell us that the system is trying to achieve something that it's unable to make set point. We also remove statistical outliers. So times like when the sun is shining on a sensor or someone turned on their computer that's sitting right next to the sensor, when the temperature reading is being influenced, that can be excluded. All right, so what does this mean? So think about the different outcomes you might have from this sort of analysis of the zone. You might have a zone with a very large learned range. You might have a zone with a very small learned range. You might have a zone where the learned range cannot be determined because the system never functions properly during the observation period. So let's take this out of hypotheticals and look at the learned ranges for each of the 10 zones from our previous example. So here we see the 10 learned ranges for each of those 10 zones. The 3 zones that had a fault condition that were triggered have been highlighted in red. We also see a blue dot indicating the current temperature and a dashed line indicating the current set point. So which zone should I fix first? Well, it turns out that none of the zones where a fault was triggered was actually the problem. And we're going to take this back to one of our original operability examples. So this was the site where the customer mentioned that he did not think that the boardroom is operating correctly. The air handler serving this space is maintaining a discharge air temperature of 59 degrees. Can we make it lower? Basically, that 59 degrees doesn't seem like it's low enough to cool the boardroom. Well, the boardroom is served by VAV 1-2, which seems like it's right at set point and doesn't have a fault condition triggered. This is where process and expertise become important. The fault detection rules did not pick up that the boardroom was not operating correctly. That learned range of 70 to 74 are the default values. So when we see that, we know that the zone has not actually learned anything. All readings have been thrown out because there was some operational condition. It turned out the temperature sensor had failed, which resulted in the VAV box not working correctly. Fault detection rules didn't pick this up because it appeared that the temperature was at set point. And note that many fault detection systems only look at point values and not at what I would call point metadata, like status and priority. It also didn't show up on the graphics because a virtual point was on the graphics instead of the actual sensor point, and the virtual point wasn't failed. So nobody noticed. So all that being said, this could have worked way better, right? We were able to properly diagnose why the system wasn't working correctly. We were able to use some of the data from the machine learning algorithm. But why did it take the customer noticing a problem before we took action, right? How could this have been flagged proactively and corrected? What if there was nobody who understood how the algorithm worked and didn't recognize that 70 and 74 were the default values? An improved process, coupled with the right expertise, could have addressed this issue before we reached the brink of customer intervention that would have defeated the optimization algorithm. Here is our other example from earlier in the presentation. This is a peak demand limiting algorithm has been deployed to keep customer power consumption below a set point to reduce demand charges. So in the message from the customer, this is the optimization algorithm they were referring to. The customer has erroneously concluded that this algorithm was controlling static pressure set point on his air handlers. So the problem that he observed, that static pressure is down too low, I don't know why he thought it was too low, and it was not the result of the optimization algorithm because the optimization algorithm does not control that parameter. But Why did the customer conclude this? What was the underlying issue that was seen that resulted in a complaint about static pressure set point in the first place? Additional training and better communication on the part of both the service provider and the customer could help resolve the underlying issue more quickly. So this takes me near the conclusion, which is that we have these great emerging digital tools like digital twins and machine learning. But in order for any optimization and analytics solution to work, there must also be a process in place for experts to interpret and for technicians to respond to the issues. There are many options in the market for fault detection services, which will use data from your system to identify equipment that is not performing on an ongoing basis. That service provider may also provide expert triage of these issues to provide a more actionable to-do list of corrective actions. However, far too many building operators contract with these services without having a plan, and more importantly, a budget for acting on those findings. So I would ask the folks on the call who said we keep getting the same fault detection report to reflect on why that might be. Are we actually attempting to fix any of the issues that are flagged, or do we just take the report every month and don't have a plan in place and a process in place for acting on those findings? I will say for my part, I have seen many customers cancel their fault detection contracts because they were receiving the same report every month or quarter and didn't feel like they were getting value. It's true that they weren't getting value, but the reason is that the analytical services don't deliver value until and unless the findings are acted upon. And replacing rule-based fault detection for digital twins, for machine learning, is not going to address that fundamental issue that you still need a person to go turn a wrench when something is broken. So in summary, before we get to questions, kind of bring it all together here. Modern buildings are only going to be able to achieve the levels of efficiency required for customers to achieve lofty sustainability goals through complexity. This is not going to be avoided. The complexity is not going anywhere. This means that we need to be thinking about how to maintain the high levels of performance of these complex systems when designing our strategies. This can be done by leveraging digital twins and machine learning to both deliver optimization and insights into how systems are performing. These insights need to be delivered to building operators in near real time so that the consequences of action or lack of action are understood by these key stakeholders. In all cases, we should not expect that machine learning or AI or software of any kind is going to be able to replace expertise. And we need to keep in mind the importance of a process that actually fixes the things that break in these complex systems so they continue to work as expected. So that is the end of the prepared remarks, but I'm happy to take any questions that came up at this time.
Thanks, Jesse. We actually do have a couple of questions. The first one is from Jonathan, who asks, do you think that that supply air temperature reset and static pressure reset strategies can be effectively used together?
Good question. The answer is they have to be used together, right? Because they relate to one another. When I change my supply air temperature, it influences the amount of airflow that I need. And changing the amount of airflow that I need will change what my right static pressure set point is. So really these strategies should be combined into a single, let's call it air handler heating and cooling delivery optimization solution.
Okay. We have a question from Tim, who asks, can you speak to the ROI of building and maintaining an operational digital twin for this purpose? He goes on to say, this type of system appears to be quite expensive to install, set up, and maintain. So basically, what what type of savings, and I suppose not just savings, but other benefits would you expect?
Mhm. So if we go back, if we think back to that first slide where I showed how the buildings have, let's call it, gotten worse over time, right? Which is that we started with very efficient buildings using about, I think it was 33 kBT per square foot, and that's risen all the way up into the 40s. That's about a 25% increase in HVAC energy use that can largely be addressed through very low cost corrective actions, right? Because we don't have to expensively retrofit our systems with, new ductwork, new VFDs in order to achieve that improvement. We simply have to identify why the sequence isn't working as intended and address that key issue. So the ROI is actually quite high because even though there can be some expense involved in the initial install and setup of a software solution, we are still talking about software, and the corrective actions that we identify are definitely going to be very low cost, very high ROI to address.
So I personally had a follow-up question to that.
Okay.
You were speaking earlier about how the need for expertise, the need for the ability to understand the analytics doesn't go away when you have AI and learning models and that sort of thing in place. But I imagine it does change, how that expertise, what kind of expertise is required and how that's put in place. So could you say a little bit about that, about how that's changed,
Mm-hmm.
the kind of expertise that's required?
It really requires you to be very flexible. So this is one of the things that I do is I spend a lot of time teaching new engineers how to execute these sort of services. And one thing I see when they come out of school is that they're expecting things to be, I would say, pretty rote. And you can't really follow a script to do this. So that both puts a premium on expertise. It does make it a little bit more harder to achieve because what you have to do is you have to truly understand how your customer's individual building is supposed to work, how that optimization algorithm was supposed to impact it, how that optimization algorithm works, and then interpret all of that together in order to figure out this is what's going on, this is the corrective action that we should take.
So I could imagine that you still need that ability to interpret that information, but then also there's no real replacement for that practical experience that someone has with their own building and your ability to
Mhm.
extract that information from them.
That's right. There was not talking about digital twins or anything, but just kind of the diagnostic process. There was a customer very early on in my career that was, I'm not going to name names because it'd be a little embarrassing.
Please
They
don't.
had I won't. They had a very large chiller plant, and water went out the chiller plant in two directions to two different buildings. And they would always run two chillers, one on this side of the building and one on the other side of the building. And they said, if we don't run a chiller on both sides, then the water exiting on the west side gets too warm. I was like, well, that doesn't make any sense. And he's like, here, I'll show you. And he turned the chiller off. And sure enough, the water leaving got warmer. Right. So he wasn't wrong about what he was seeing. Right. He was correctly communicating to me what was going on. But his solution of I have to turn another chiller on without spending some time to understand that and look into it. I mean, they were spending tens tens of thousands of dollars a year running that extra chiller when they didn't need to, because as it turned out, a differential pressure set point in the west building was set too high and they were short cycling water. Right. But
Yeah.
like that sort of expertise and diagnostic process and understanding, that's the expertise that no software is going to be able to replace. And that experience of that customer's building is something that you're always going to need to be able to work with and extract.
So I just want to just take a moment here just to remind everyone, if you check the chat, there's an address there for the ability for attendees to download the slides. I know people are very interested in the slides, and I just want to let people know that if you check the chat, there's a link to the Dropbox. So Back to the questions. Brian asks, has anyone ever used a system like this to automatically generate trouble tickets in a CMMS?
It depends on what you defined as automatically. I think you generally want someone to look at those issues that are being generated before going to a CMMS. I think CMMS is a great way to manage, especially in a complex organization. What are the issues that we're working on? But you don't want it to get clogged with noise, to get clogged with nonsense. And that's one of the big issues with fault detection is it will generate a lot of faults. It will do the thing it says it's going to do. It will detect faults, and you need someone to triage that and say, is this a real issue? Is this a nuisance issue? Is this something we already knew about? Are these two faults the result of the same issue? And I just want that one issue to go into the CMMS. So that sort of expert triage should happen before going into any sort of ticketing system. But there are, I know we do it. There's lots of different ways that that incident can be managed once it's triaged.
We have someone, it's kind of funny, it comes across, it says anonymous attendee. It says, in a building with hundreds of VAV boxes, there is a high possibility of few oversized and undersized boxes. Is static pressure reset strategy a good approach for such buildings?
I'm going to give the engineer's favorite answer and say it depends. And what it depends on is, so let's say I deploy a machine learning algorithm to optimize the static pressure in a building like that. What it's going to do is it's going to identify, here's your oversized and undersized boxes, and here are the critical ones that are going to drive the behavior of the static pressure reset algorithm. Now, you have the choice of, do I just let that room be hot? Do I take some corrective action to address that deficiency and put in a right size box and fix it? Or do I turn the optimization off? Right? Those are your options. So I think it is a good approach. And I think, my recommendation would be that you can do a diagnostic of how your VAV boxes are performing prior to deploying that strategy, kind of see where you're at, and then decide, is it going to be a worthwhile investment to address those deficiencies to make it work?
And the anonymous attendee came back and said, thanks.
Great.
So, and if anybody that submitted a question, I should say, has a follow-up question, feel free. Mohammed asks what you think the best online or good online training resource for building engineers and technicians on this topic specifically.
Oh, you mean other than this webinar?
Right.
One of the reasons I wanted to do this topic is I haven't seen a lot of training online on this topic. I think it's a good question. We do a lot of the training in-house for our engineers. We, have developed a lot of it ourselves. But I might take that as an action item, see if there are any public resources that can be that are already available to help with these sorts of topics.
Well, and then also this webinar recording is going to be available within a week. So, it's something to bear in mind, that, Mohammed, if you want to share this with any colleagues, this might help you formulate some questions also that might get you some good resources. So Jesse, what are some other challenges to optimization that maybe we haven't gone into here? I know you're kind of trying to be focused, but is there anything that hasn't come up specifically in your presentation that maybe you want to shine a light on?
I would say there's one other challenge that I didn't focus on, but it's more of a practical challenge, which is I think one of the previous questions mentioned the potential expense associated with deploying these algorithms. They aren't necessarily expensive because a lot of these are deployed in the cloud, right? But what that does is it brings with it its own risks, which is I now have a building automation system that I need to connect to the cloud and open up that connection in order for data to be exchanged and even for closed loop control to happen.
Right.
And many customers, I would say, are very reticent to taking that leap. I will be honest and say that the HVAC industry does not have a sterling reputation on this topic. I think folks might remember, or if they don't, I'm about to remind them that maybe 7 years ago now, Target had a hack of their credit card system, and that attacker got in through the HVAC system.
Yeah.
That was right. So there's real reasons, but that folks are reticent to do it. But I think if you see enough value, and like there really is a lot of value both to achieving sustainability goals and decarbonization and just reducing operating costs, those risks can be mitigated with some really basic steps.
Okay. So we have Justin has come in and he asks, what calculation do you use to reset the data set point for an AHU and a VAV system?
I mean, there's a number of different strategies for this, right? I think ASHRAE's GPC 36 is their high performance building standard, and they have a sequence that I think a lot of engineers use that programs a sequence, directly into the building automation system to reset both static pressure and supplier temperature set point. There are also options that use machine learning or AI out there. There's several of them out there that are taking the data from each of the VAV zones, and many of them I say are highly proprietary about how they're achieving this. But you could say all of them are essentially evaluating the same type of approach, which is my worst case zone that's driving additional cooling, and then changing my discharge temperature sensor in response to the demand from the zones. One of the reasons it is a complex problem is because, as one of the other questions mentioned, there are hundreds of zones that you got to rely on feedback from. And if you just take it straight off the box, it says, if any of them need more cooling, I'm going to drop my discharge air temperature. What you mostly end up with is a constant temperature system because there's always one that says it needs more cooling. So it's a complicated question.
I knew this was going to happen.
Well, I'm glad the record was corrected that it was not that it was the work order payment system of the HVAC vendor. Unfortunately, that correction has not done our industry any favors. But I do appreciate correcting the record for sure.
Yep. Yeah. I was just gonna say I worked in retail at the time, and I knew it was slightly different, but close enough. Okay, so I just want to check if there are any more questions. Yeah, hard to correct rumors. Agree. Okay, I just wanted to check, are there any other questions before we get to the next part of our presentation, which is me basically telling you what's up next. Okay, so my music teacher used to say, always say bacon, eggs, and ham before you bow. Yep, great. So that's a wrap for this webinar. Thanks very much, Jesse, for your presentation and for the discussion. And thanks again to our sponsor, Siemens. Up here on the screen, I just want to call your attention to technical training that we are going to be holding this week, actually tomorrow and Thursday. We're doing virtual O&M training for facility engineers and managers with Al LaPera. He is an expert presenter par excellence. And if you're interested in registering, you can go to energymanagement.mgmt.org, or you can send an email to info@energymanagement.mgmt.org and let us know you're interested, and I'll get right back to you. Okay, so thanks again, Jesse. That was a great presentation. I really appreciate it. Good questions from the audience and good discussion. So thanks again. And that's it.